Hello everyone. Today our topic is reactions and solutions. This is MSc Chemistry, first year. As we know, the kinetics of reaction taking place between ions deviate considerably when compared to the kinetics of reaction taking place among non-electrolytes. These deviations are mainly due to considerable electrostatic force exerted by each ion on the other ion. The velocity constants of ionic reaction depend upon the charge of reacting ions and also on the ionic strength of the solution. So let us consider the effect of electrolytes on rates of reactions. In detail, we'll be studying today about primary salt effect. According to transition state theory, the reacting ions first form an activated complex, which is in equilibrium. With the reactant, and then this activated complex decomposes to yield the products. So the rate of reaction is determined by the concentration of activated complex. Plus B of ZB form an activated complex which in turn forms the product. Here A and B are the reacting ions. ZA, ZB, these are the charges. AB is the activated complex. ZA and plus ZB are the charges of this activated complex. K1, K2 and K3 are the velocity constants. Now, according to law of mass action, the equilibrium constant is given by K star is equal to A of AB divided by A of A dot A of B, where K star, or you can say K1, K2 is the equilibrium constant for the process A plus B going to A B. A of A of B, and AB. These represent the activities of reactants A, B, and activated complex AB. But as we know, activity is we know that activity is concentration into activity coefficient. That is, A is equal to C into gamma. So now the expression for equilibrium constant will change to K star is equal to A of AB will now be written as C of AB, and A of A will now be written as C of A dot C of B into this value gamma of AB divided by gamma of A, that is activity coefficient of A, into activity coefficient of B. Here CAB, CA, CB, these represent the concentration of AB, A and B, and gamma AB, gamma A, gamma B represent the activity coefficients of AB, A and B respectively. So now the rate of reaction is equal to K3CAB. Substituting the value of CAB into this equation, we get the rate of reaction as K3 K star. This whole thing will be multiplied with this. This whole thing will be multiplied with this. And this whole thing will come on the lower side. So we get what is called as CAB. And this value we will substitute over here. CA, CB, into gamma A, activity coefficient of B, divided by activity coefficient of AB. That is this K3 K star. Now we will represent it as KO, K0. The rest other things will come down as it is. That is concentration of A, concentration of B into activity coefficient of A, B divided by AB. So as I told, K0 is equal to K3 K star. The experimental rate of reaction is given by K R, concentration of A, concentration of B. From the above two equations, what we can conclude is Kr is equal to K0, activity coefficient of A, activity coefficient of B divided by activity coefficient of AB, where we can say that K0 is the rate constant at infinite dilution. And at this infinite dilution, gamma A is equal to gamma B is equal to activity coefficient of A B will be equal to 1. So it is evident that any added substance which alters the value of activity coefficients of reactants and activated complex will change the experimental rate of reaction. Now, taking logarithms, log of Kr is equal to log of K0 plus log of activity coefficient of A, coefficient of B divided by activity coefficient of A, B. But according to Debye-Huckel's theory, the activity coefficient of an ion of charge Z is related to the ionic strength mu of the dilute solutions by the expression minus log of gamma is equal to 0.509 Z square under root of mu. This happens at 25 degrees centigrade. So, for A, B and AB, the above expression can now be represented as log of gamma A is equal to 0.509 ZA square under root of mu. Similarly, for log of activity coefficient of B, we can write it as 0.509 Z B square under root of mu. Similarly, for log of activity coefficient of gamma AB, we can again write it as 0.509 0.509 in bracket of ZA plus ZB the whole square under root of mu. Since we have got all these values, we can substitute all these values in the expression for Kr. That is, log of Kr is equal to log of K0 minus 0.509 ZA square under root of mu plus 0.509 ZB square under root of mu minus because this we will be taking up, so we will write it as minus 0.509 bracket of ZA plus ZB the whole square under root of mu. On opening the brackets, log of Kr is equal to log of K0 minus, we will take 0.509 and mu, we will take it as a common outside the bracket. What we are left out with ZA square plus ZB square plus ZA plus ZB the whole square. That will be ZA square minus plus 2ZA ZB plus ZB square. Since there is a negative symbol outside, it will get multiplied with all of them. And so we will have minus here, minus here, minus here, bracket closed. Therefore, log of Kr is equal to log of K0 minus ZA square plus ZA square minus ZA square gets cancelled. ZB square minus ZB square gets cancelled. What we are left out with 0.509 into 2 ZA ZB, that is log of Kr is equal to log of Ko minus, when we multiply it we get it 1 point, and this minus and this minus. Minus into minus will become plus. So we have 1.018 ZA ZB under root of mu. This equation is known as Bronsted-Jerome equation. Since the variation of specific rate constants with ionic strength depends on the charges of the reacting species, three cases arise. First case, it arises when ZA, ZB becomes 0. It means that one of the reactants has no charge. That is, it is a non-electrolyte. Then the rate constant would be independent of ionic strength. We can take an example. CH2I COOH. When it is treated with thiocyanide, we get CH2 CNSCOOH plus I minus. Here, this is a non-electrolyte. Hence, Za into Zb will be 0. Let us see the second case. It arises when Za Zb is positive. It means Za and Zb are of same sign. The rate constant for such reactions would increase with mu. Let us take an example here. S2OH 2 minus. I plus will give us the product. Here, the value of Za and Zb is plus 2. Although both ions have negative valency, let us see another example. A complex of cobalt CO NH3 Br when it is along with Hg plus 2, we get the product. Here, the values of Za and Zb is 4. Hence, the salt effect is positive. Lastly, the third case arises. Now, here it is positive, here it is 0, here it is positive. So, the last case will be when it is negative. So, it means that Za and Zb are of opposite signs. For such reactions, the rate constant would decrease with mu. Here, it would increase with mu. Peroxide H2O2 plus H plus plus Br minus. We get the products. For this reaction, Za ZB. They will be equal to -1. One more example let us take of cobalt complex. When it reacts with OH minus ions, so here again you can see Za and Zb is -2. Hence, here the salt effect is negative. That's it for today. I'll be coming up with secondary salt effect in my next video. Till then, keep watching.